Good evening, and we'll change tracks a little bit, go a little bit into technology, but we'll also try to talk about relevance to business from the lens of quantum computing. Just to set the context, the world is getting smaller every year almost, right? And we can feel it. But as it's getting smaller, we are also realizing the big problems we face as a community, as a global community, whether you look at climate change, whether you look at supply chains, whether you look at sustainability, and some of these are extremely hard problems. Part of it is about humanity coming together to solve it, but part of it is actually solving and coming up with solutions through innovation, right? And our MC actually gave a great intro to Summit. This is just representative of the supercomputers we have, and these are amazing systems that can do amazing computational tricks. They can do molecular simulations, climate simulations, nuclear simulations, and those have tremendously helped us in advancing technology on so many different fronts because of what these computers can do. So then the question is, are there still computational problems that are intractable, that these amazing supercomputers can't solve or wouldn't be able to solve, let's say, after 5 years, once you have 10 times the more powerful supercomputer that comes out. Turns out there indeed are such problems, and to make it real, here are some examples, and this is just few out of many. When you think about batteries, which are so central to the future of where we want to go with tackling climate change and the energy crisis and renewable energy, without being able to store energy, we really don't have a future. And today's batteries are really much more advanced than say 20 years ago, but they need to go much, much further, and it's hitting a plateau. Not a plateau, but the scale is very hard to push in terms of battery efficiency. And one of the key challenges there is, can you compute exactly what happens inside, say, a lithium-ion battery? How does the cathode and anode chemical reactions happen? And can you change the chemical properties to make it 5% more effective, or have it increase the density? Going to the level of accuracy you need there, supercomputers cannot handle it. Similarly, if you look at green hydrogen, India is making a big bet on that, as we know, another big component of our collective future. Likely relies on our ability to have these catalyst materials that can convert carbon dioxide ultimately into some useful hydrocarbon like ethanol or something. While this has been proved and can be done, it needs to become much, much more efficient by many factors to address the needs of a country like India, even at some kind of meaningful scale. Again, you come down to these chemical reactions that are happening in the way carbon dioxide atom is broken and hydrocarbons are made. You need to simulate the quantum physics of that chemistry. Supercomputers cannot do this. You look at optimal routing, a very business problem. When you have large complex optimization problems, and we'll talk about what ExxonMobil is trying to do here, there are so many combinations that you have to search through. The search space can become so large that once again you run into a domain where it becomes challenging for supercomputers. Another example is drugs, healthcare. We know antibiotic resistance is becoming a major issue, and if you want to come up with new classes of antibiotics that can address this significant challenge, again you need to be able to simulate molecular dynamics to look for those structures that can address this problem, new kinds of antibiotics. All of these are now hitting a domain where it's very challenging even for the most powerful supercomputers to be able to simulate these in any kind of reasonable time that would be useful to us. And the reason is that the model of computation we have since the 1940s or even before that we still use is this model of using zeros and ones to represent information. And so when you have what's called a bit representing information, it can either represent a 0 state or a 1 state. If you want to represent lots of combinations, let's say in your routing problem, right? Or if you have some chemical simulation for an atom which can take infinite number of states in quantum physics, you start going into the realm of so many bits and storage required that it goes into like the number of atoms in the earth, right? And no supercomputer has that. And so we are running into the challenge of that computational model, and qubits or quantum bits offer a completely different way of doing computing, of representing information, where instead of saying that I will have a memory location that stores 0 and 1, imagine that you have a memory location that can store infinite possibilities that that variable can take. Now you can do calculations on all of those possibilities in parallel, and you can have this tremendous parallel scale of computation that is required for the kinds of problems we talked about. Of course, how you do it, how do you create those circuits, how do you create those materials that can do this is a significant technology challenge, and many players are trying to address it. There are many ways to do it. The bet that IBM has made is with something called superconducting qubits, because they offer a general model of computation. And if we can address this, we can actually address many of the problems that I talked about on the previous slide. One thing worth noting is quantum computers are now and have been for the last 7 years accessible just like any other cloud-based computing service. IBM was the first one to put it on the cloud, and today we have seen more than 2 trillion quantum circuits have been run on it, and millions of, I'd say hundreds of thousands of users. In fact, India is among the top 5 in the users that we see coming from India. So there's tremendous interest in the technical community and students out there to just self-learn and use these things. On the enterprise side and the use case side, kind of getting to the more interesting part, of how this may be relevant, we are seeing many clients across the world, across different industries, starting to look at, okay, as these quantum computers become real, they are taking time, they are real, but to scale up to the level of enterprise use, it will take a few years. Can we start mapping some of our business problems into this new computation model? Because the way you used to write, an operations research or an optimization model using logic in bits is very different from how you will write it in qubits. So there is a lot of research to be done that how do you model your problem using the concepts of qubits, and there are many clients who are starting to look at it. Broadly speaking, the use cases fall in these 3 areas. Either you're trying to simulate nature itself, like the chemistry examples that I talked about, that's a killer place for using quantum computing, or you're trying to find complex structure within large amounts of data. So it's not so much the data handling, but looking for patterns where there might be trillions of different patterns, right? And being able to do that parallel computation, that's the power. Or doing search and optimization, like routing problems or other kind of optimization problems where you have such a large search space that if you could represent many possibilities and do a parallel computation with these qubits, you can figure out an advantage. Broadly speaking, these are the 3 categories of problem areas where quantum computing can have an advantage. And IBM has something called the quantum network, where enterprises, academic institutions, government bodies, all these organizations who are interested to actually get hands-on with quantum computers and do the research to figure out how do their use cases of interest, how would they map, and can they come up with algorithmic implementations that promise that advantage than classical computing. And today we have over 250 members across the globe who are doing this work. So it's tremendously exciting to see the spread. Just some examples, Mercedes-Benz has been one of the leaders here looking at battery technology, specifically what we talked about earlier, where lithium sulfur batteries hold a lot of promise, but we need to figure out how to control the chemistry, how to get the chemistry right so that you can get all the metrics for the battery right, whether it's density, life, number of cycles that you can charge and recharge, all of that. And so they're looking at how do we do a better job of simulating that chemistry inside the battery, how the lithium and sulfur bonds are broken and recreated using quantum computing. ExxonMobil has a tremendous challenge with the amount of liquefied natural gas that they have to ship across the world. And they have these 500 or so ships, and they have to map out exactly what route each ship is going to take from which port to through which port to which other port, taking into account all the variables that happen in terms of port logistics and marine logistics and weather situations, supply and demand situations. And if you want to model this whole optimization problem accurately, it's out of scope of today's classical computers. They're looking at how can we model this using the quantum concepts. If you look at Boeing, Boeing is doing actually a couple of different things, one of which is trying to look at modeling corrosion in the materials that are used for the aircraft structure, and if they can do a better job of material design to minimize that corrosion that happens, that can go a long way in terms of their aircraft durability. And JP Morgan Chase from the financial industry side, looking at using quantum amplitude estimation for different things like option pricing, right? And for those of you who knows option pricing, it's a highly probabilistic kind of a complex optimization problem to choose the right prices based on all kinds of variables and future predictions of scenarios. Again, another area where the concept of quantum computing holds a lot of promise, and they're trying to see how they can model that with quantum computers. So these are a few. I thought it has a good spread of industries, so it might give you a flavor. It's becoming real in India, which is extremely exciting. And about last year, IIT Madras became the first quantum innovation center, joining the IBM quantum network, starting to use the world's best quantum computers that are available through IBM Cloud, and doing research in this area, working with our researchers in IBM, and also doing a lot of education. So we do a lot of joint education programs through NPTEL and other kinds of courses. It's sort of an interesting tidbit that IIT Madras was also the first institution in India to bring the IBM mainframe here many decades ago in the country. They are also the first organization to bring the quantum computing here, if not the computer. And we are seeing a lot of interest with the National Quantum Mission picking up, announced this year. We expect that next year a lot of those projects will get kicked off with the 4 different hubs that the government is planning. And I think we will see a lot of excitement in this area, a lot of engagement, both from academia, from government, and hopefully also from industry. As industry starts to see the promise, starts to think about competitive advantage at a global level and not just business as usual, right? And that's what we see happening. So looking a bit ahead around what's happening with this technology. So IBM did something that actually was sort of made me nervous when we first did it, which is we published a roadmap and made promises of what are we going to put out every year for the next 5 years or so in terms of the advancement in quantum computing, right? And doing this at a phase where so much is unknown about how to address the problems, the technological problems of creating these superconducting qubits, controlling them with microwave circuits and all of that. But my colleagues in IBM Quantum have been amazing at it, and this year, just a week or so ago, they published a longer development roadmap that goes all the way to 2033. So you can see there's a development roadmap at the top, there's an innovation roadmap at the bottom. Today we are of course at 2023, and if you look at where things stand, there's a couple of different ways of building these superconducting qubit processors or quantum qubit processors. And we had a breakthrough this year where for the first time IBM showed how to combine multiple processors using quantum communication. So we have broken the multiprocessing barrier. Now that is critical because there's a limit to how many qubits you can pack on a single chip. These qubits are not as small as transistors, they're actually big. So you can only go so far. And if we need to get to 1 million qubits, that's not going to happen on one chip. So now we've gotten modularity at a chip level, which allows us to scale. We also announced the Quantum System 2, and I'll show a little bit about that, which achieves modularity at a system level, right? And this is critical for us to be able to scale up quantum computing, just like we did with servers. You know, if you had to pack everything in a single chip and a single server, and your whole data center was one chip and one server, that's very limiting. What enabled us to digitize and everything is because these were modular systems. You can add on, plug and play, keep adding servers and building out these data centers. We need the same kind of system architecture modularity with quantum computing. And so that was demonstrated and is now in product as of now and is being rolled out to IBM Cloud. At the software level, there's a lot of work that has happened. There's a lot of work that needs to happen because these things need a runtime layer, right? This entire processor and operating system, using traditional terms, is completely different. The middleware has to be completely built up from scratch. All of that is happening. And then on top of that is the development platform, because at the end of the day, this is useful only if you have a developer ecosystem that is writing those Python programs using quantum computing concepts to solve all those problems. And so from day one, at least in IBM, we have taken the approach of creating a very familiar programming layer, which is based on Python. It's completely open source. It's called 𝗕𝘂𝘂𝗺. In fact, it's so open that we have non-IBMers in India in the community who translated all the 𝗕𝘂𝘂𝗺 books to languages like Gujarati and Hindi and so on, right? So it really has taken a life of its own. And that is the development platform where a lot of innovations are coming to accelerate developer productivity, to create higher levels of abstraction so that it's easier and easier to program these things. So hopefully that gives you a sense. One important point I want to make is earlier this year, some of the IBM researchers working with the University of California, Berkeley researchers demonstrated what we call quantum utility, right? So until now, there was a promise that quantum computers will be able to solve a problem that classical computers find hard, and it was based on all of the theoretical understanding of what we can do with these things. But there was a particular scientific simulation of quantum physics that for the first time we were able to demonstrate a quantum computer of 127 qubits being able to come up with an answer in some practical time, whereas the corresponding supercomputer that UC Berkeley used could not, right? So we don't call it quantum advantage here because to get to advantage a lot more has to happen. But this demonstrates usefulness. This shows that there is usefulness in quantum computers and demonstrates it with a real problem. So we believe we've entered the phase of what we call quantum utility. And so the next 5+ years is really going to be about how do we demonstrate and scale up this usefulness of quantum computing. And all of this innovation and development you're seeing here, from an IBM perspective, we're focused on demonstrating increased usefulness of quantum computers, right? So let me use a video here because I think it's a really nice video to show you a bit about the new quantum system 2.
Introducing the IBM Quantum System 2, the world's first modular utility-scale quantum computer system. Quantum System 2 was designed to tackle complex problems that lie far beyond the reach of today's classical supercomputers. It stands 15 feet tall and operates in a near-perfect vacuum at temperatures colder than deep space. Initially powered by 3 133-qubit Heron processors, Quantum System 2 is fully upgradable to the growing line of utility-scale QPUs that IBM will be releasing over the next 5 years. This is the world's first modular utility-scale quantum system. So in addition to talking about physical qubits, we now need to be concerned with circuit size. By the end of 2024, each of the 3 Heron processors in Quantum System 2 will be able to process a remarkable 5,000 operations in a single quantum circuit. But the real triumph of Quantum System 2 is its modular design. Our new quantum coupling technology will allow multiple Quantum System 2s to connect together to create systems capable of running 100 million operations in a single quantum circuit. Continuing down this path, we plan to realize a system capable of running 1 billion operations in a single quantum circuit by 2033. That's why we call Quantum System 2 the building block of quantum-centric supercomputing. Today, our clients and partners are already using our 100-plus qubit systems to advance science, surpassing brute force methods deployed on the world's most powerful classical supercomputers. And soon, they expect quantum applications offering unprecedented business value. Our mission is to bring useful quantum computing to the world, and it starts with Quantum System 2.